Hello YouTube, welcome to this video. So in this video, I've actually made a BasePipe class, and as you can see, it's actually being run properly. Okay, the BasePipe class is an actual class now. Okay, it's an actual class that that can be put in used as an object. Okay, and it contains all the friction factor correlation. So let me take a look. There's a warning. Oh, check numbers is declared but never used. Okay, whatever. Okay, so you see there's a BasePipe without pipe factory. Okay, so this is the name of the test which I just used a this.cout over here. In case you didn't know what this cout here is, it's a custom function that helps me console write line into XUnit if I ever pop up on Windows OS. Because there should be some sort of I output helper. Okay, some sort of I output helper. As you can see here, I need an I output helper to be fed in as a dependency injection. All that complication is just to make sure it prints properly. But yeah, this is the test name. I put 1.45 so-called volts, but now it's in kinematic pressure unit, so it's meter square per second squared. And then this becomes the mass flow rate. It's about 3660 kg per second of mass flow. That is a that's a huge amount. Okay, so do note that that's the kinematic pressure is 1.45 meters square per second square. If I and this pipe is actually having some kind of water, so that equates to about 1.45 kilopascals. That's a lot of pressure for one pipe. Pressure drop for one pipe. So you can imagine the flow through this pipe must be a lot for this much pressure difference to accumulate. However, I have not checked whether this value is possible just yet. And that will be actually the next part. The more interesting part is actually what goes on underneath the hood. Okay, so what goes on underneath the hood? All right. Okay, let's go to BasePipe. Okay, BasePipe is the class is basically the same. It's like my mod pipe, except I changed the names. Nothing else here really changes. The more interesting part is in the base parameters. Okay, base parameters is actually done using the EngineeringUnits package. Okay. Yeah, so it's done using the EngineeringUnits package. And this actually comes from, oh, what is this here? Okay. Yeah, this is done using the EngineeringUnits package. All right, EngineeringUnits package. And what the EngineeringUnits package does is to force you to use units. So for example, when I have a hydraulic diameter here, I can declare a length object, and it's basically I need to specify a quantity right here, and I have to specify a unit right here. So this is in SI units, which is meters. Pipe length is also in SI units. But absolute roughness, I can actually dimension it using millimeters, as you can see here. But anyway, so all of these things, I actually just plug it into the base parameters class right here. Base parameter class. I also give ways to calculate cross-sectional area, which is pretty useful if you want to calculate Reynolds number from the mass flow rate. Roughness ratio here. Okay, that is absolute roughness. Change the units to SI, divide by hydraulic diameter, change the units to SI. Right, I have yet to actually test whether this actually does the unit conversion correctly, but I will just leave it for the time being. Okay, length to diameter, okay, pipe length as length unit SI divided by hydraulic diameter as length unit SI. So whenever I have what do you call it? Whenever I have dimensionless quantities, I will use the double for them. Otherwise, as far as possible, I will try to use these EngineeringUnits to make sure that I don't have careless mistakes when it comes to that. Okay, so these two are kinematic and dynamic viscosities of water. Okay, kinematic viscosity is in the centistokes unit, as you can see here, centistokes unit. So I just got it from the engineering toolbox, water dynamic and kinematic viscosity at 18 degrees C. It's a very simple reference value. Okay, so water kinematic and dynamic viscosity is over here in the base parameters, and there are as kinematic viscosity and dynamic viscosity units. Okay, nothing too much to see here except those. Most of the not magic, but most of the work's done over here. All right, at least part of it. So I've done up a README file for this, so you can see right here how it goes. I have written actually some notes. Okay, so the first thing first actually that happens is that, okay, what at the end of the day are we doing? Okay, so at the end of the day, we want to perform this method right here, this dot elements add. So it adds all the correct Jacobian partial derivatives to the Jacobian matrix, as you can see here. Okay, dm, dpa, dm, dpb, so on and so forth. Okay, so that's important. You can take a look at the pipe fluid flow, the theory, how to see how this is actually derived, or maybe we'll go through that sometime later. Okay, so the Y matrix is over here and the right hand side vector is here. We'll talk a little bit later about how they are calculated, or maybe we'll do it in this part. Okay, so this is where the Jacobians actually calculated. So instead of for modified nodal analysis, we actually differentiate the current part. We do a partial derivative of the current with respect to the pressure at each, or at least the voltage at each node. So equivalently, for mass flow rate, we will differentiate the mass flow rate with respect to the pressure at each node, and I'll use the calculate. Okay, the Jacobian object will have a method called dmdpa at each of the nodes, and then it will just calculate all of that. So what's the Jacobian object? The Jacobian object is over here where we have all our fanning friction factor nodes, stuff that we discussed in the last video. Of course, there's a little bit more code there than just simply calculating friction factor. We actually calculate the Jacobian outright. So that's where all the things happen. And what do you actually fit into the object? We have things like what? Cross-sectional area. Cross-sectional area. Fluid viscosity, hydraulic diameter, pressure drop, absolute roughness, pipe length, fluid kinematic viscosity, so on and so forth. Okay, so these are the important things that we are feeding into this function, and it's supposed to return us the appropriate partial derivatives. So that's how the code runs. Okay, so where do we get all these values from? Okay, where do we get all these values from? Okay, we get it from our base parameters. Okay, we get it from our base parameters. So as you see just now, okay, B sharp. As you see just now, our base parameters will have things like cross-sectional area. You have things like kinematic and dynamic viscosity, as you can see here. I don't know whether the highlight's helping or not, but that's where you all get the stuff from. And this will be in, of course, proper dimensioned units. Okay, so see, even mass flow rate, all of this is supposed to be properly dimensioned. Okay, so these are the engineering unit objects. Okay, the only time again where I try to use doubles is when I calculate dimensionless parameters. But over here, I don't really have a choice. I have to use doubles here instead of a dimension unit, because at the end of the day, I need to feed them into the Y matrix, as you can see over here. Okay, I need to feed them into the Y matrix. Okay, so that's what this part is doing. Over here, this is to make sure that there is some kind of minimum value for each gradient. If not, if we have 0, 0 for all of the value for all of the derivatives there, the algorithm will just get stuck. Okay, and that's one of the quirks of this code, but we'll talk about that later. Let's just talk about the inner workings first. Okay. Yes, can see the Reynolds number is a double. Okay, if visual number more than 0, then yes, let's calculate the Reynolds number. Otherwise, Reynolds number is 0. Okay, that is the thing. Okay, yeah, but long story short, Reynolds number will be a double instead of a unit kind of a thing. So as far as possible, all dimensionless quantities will be in doubles because you don't really need to guess the unit. They are dimensionless. Okay, so that's what I am. Yeah, what I'm here. Okay, so there was a particular bug within the code, which I'll explain later. But let's first take a look at what's inside the Jacobian thingy first. Okay, so the Jacobian object is over here. If we take a look at the Jacobian object, it will be okay. Jacobian. Okay. Okay. Question mark. Jacobian. So it does a backward search. Yes, Churchill friction factor Jacobian. So this is the object that I use. How does it work? Churchill friction factor Jacobian is, let me open a new tab, nurture it, and okay, I'll just open it up. Pipes and valves, the math is here, friction factor is here, the Jacobian's here. Okay, Churchill friction factor. Okay, so the so-called things, everything that works underneath is over here. So what does Churchill friction factor, how do you actually get it? Okay, it inherits methods from the Churchill mathnet derivative class. Okay, remember I was saying the last time that there are a number of ways of calculating derivatives. There's the mathnet way, which already, well, I think the algorithms are better. You don't need to do everything from scratch. Okay, so the Churchill mathnet derivatives will be under Churchill friction factor, and then you do it over here. Okay, the main difference is that we use the mathnet derivative object over here. Okay, and then we'll use that to calculate our derivatives. Okay, you can go and take a look in your own time what these derivatives. Okay, maybe I'll just show it to you. It's actually better. Okay, mathnet derivatives.cs. Okay, we use the mathnet numerics package as you can see here, and all of these are just the functions. Okay, we do a calculate function. How do you calculate the derivatives? First of all, we check the validity. Okay, is the function defined at that point? If the function is not defined at that point, probably the derivative also is not defined at that point. We'll just throw an exception. Okay, the exception will be a divide by zero exception, which is mathematically quite similar to an undefined. Okay, so if everything's okay, we just differentiate using the first derivative. Okay, we'll differentiate the function. What is the function that we are differentiating here? Okay, the function that we are differentiating is, well, not exactly put here. You have to define that function somewhere else. Okay, it's basically just the mathnet. What do you call it? It uses the mathnet derivative functions, except I kind of put some number checks to see whether the derivative is undefined. Okay, so that is pretty much it. I'm not going to go through in detail. You can go and read it up. But yeah, let's go to the last one. Okay, so here we are. What are we looking for? Things like dMdPa, right? dMdPa. So this is how we actually calculate our Jacobian. Okay, the derivative result will be of type double. Again, no choice. We have to actually use doubles because we need to put it into the matrix directly. Okay, but the mass flow rate will be dmdRe. What is the mass flow rate? Why is dmdRe like the in mass flow rate units? It's because when we differentiate Reynolds we differentiate mass flow rate by Reynolds number. Okay, Reynolds number is dimensionless, so the dimensions of this is still in mass flow rate dimensions. Okay, we need to get the mass flow rate dimensions because it's basically chain rule. Okay, we need to do a lot of chain rule over here in order to get our partial derivatives. Okay, where do we get all this chain rule thingy from? So the chain rule part actually will be more clear if we actually take a look at our pipe class, or rather math class. Okay, not here. I need to go to the pipe theory part. So let's open file, open folder, spiceSharpFluidFLowSolver. Open the libraries, trust all authors. Let me open the where is the thing? Okay, let me open one more level up. Now open this folder. Okay, so here, yes, here's the documentation. Pipes and valves. Okay, wrong one. Theory, fluidPipe theory, fluidpipetheory.md. Okay, let's go here. Okay. And yes, consider this. Consider the Jacobians we need to calculate. Okay, right? We actually need to. Right, if we take a look at the fluid pipe theory, we've gone through that a few videos back. How do we calculate the Jacobian numerically? We actually need to differentiate mass flow of the pipe with respect to the pressure. Okay, to obtain this, okay, well, we have a pressure explicitly in terms of mass flow rate, or at least Reynolds numbers. So we kind of need to flip it using the total derivative rules. Okay, so we can convert total into partial derivatives because all the other things are constant. Like, we don't expect roughness ratio to change or anything else, fluid viscosity to change too much when the kinematic pressure changes. So we can change the total derivatives into partial derivatives quite easily. Okay, so we want this dm pipe dpb, but we can get from our friction factor correlations dp dre. Okay, but we need to change it to a dm pipe dpa kind of a form. So I'm actually going to introduce pa into this derivative using chain rule. Chain rule, dp dpa dpa dre. Okay, so that's what we're going to do. So and not just that, I am actually going to introduce mass flow rate of the pipe in. So I have a dm pipe dre over here, dpa dm pipe, and the delta p dpa. So the end result we want is the dpa dm pipe. Okay, and that will actually get us very close to this thing, so that we can just invert it on its head. We'll get the answer. Okay, at least that's the hope. Okay, so the m pipe dpa, if we look at that, we'll have the delta p dpa, the m pipe dra, the delta p dre. So these are the three things we need to get. Okay, so one of them is the dm pipe dre, and this will be in mass flow units, as you can see over here. Okay, so what's this dm dre? Okay, dm dre will be will be over here. It will be of the mass flow rate units. Okay, you will need a cross-sectional area, dynamic viscosity, fluid viscosity, and hydraulic diameter. So what's the MDRE? And the MDRE is actually pretty simple. If we take a look at the definition of Reynolds number, we take a look at the definition of the Reynolds number by mass flow rate. Where did I put everything? My equations are all over the place. Let's see, go up. Yes, here we are. So dm dre, okay, we can just shift all this diameter kinematic dynamic viscosity all over to the left hand side. Okay, so all these terms, if we shift them to the left hand side and then we differentiate both sides with respect to the Reynolds number, we'll just get mu a cross sectional area times d, or mu times a cross sectional area divided by d. That's all that we will get. So it's not that this derivative is pretty trivial to actually calculate, so we don't need any anything new. Okay. I don't know why I didn't write it down, but okay. But this is what this dmdre is about. Okay, so yeah, I think maybe a good idea to put a readme here, a readme file that tells people why I calculate things this way. Yeah, but anyway, so that's what the dmdre is there for. Yeah, so the dmdre is here, and then we just need to calculate the other derivatives here as we actually do the chain rule thingy. So one of them is the d delta p dpa. Okay, delta p equals to pa minus pb, and this refers to pressure drop, not pressure change. Okay, so that's fine. Pressure drop is not pressure change. So pressure change is final minus initial. Pressure drop is the initial minus final. Okay, initial pressure minus final pressure, and PA is, I guess we can call it the initial pressure. PB we can kind of call it the final pressure, unless the flow is somehow reversed. If we do a partial derivative of d delta p dpa, and one of these pressures will just disappear. Okay, so that's what we can get. Okay, yeah, we'll just assume that thing can work. I'm not going to go too much into the math details. I just hope the code works somehow. So next step will be this d delta p dre. d delta p dre. So what is d delta p dre? Well, you see that delta p in terms of re can be so-called found here. So this is our friction factor correlation. I'm going to non-dimensionalize all the u terms here, like this u here will be non-dimensionalized into Reynolds number. So I bring all the Reynolds number terms to the left hand side. Okay, and this f here is a fanning friction factor. All right, so all of these things here, I will all of these viscosities and things here, I will just combine it into the pressure to kind of give a non-dimensional pressure. The quantity of choice I use is the Bijon number because it already exists. I don't want to reinvent new dimensionless quantities. So okay, I guess that's time to stop. Yeah, and I will not continue this video too long. I will see you next time. Bye bye.